everybody, so welcome to our next video for Unit 1, which is all about limiting and excess reagents. Now, if you took Chem 2, which a majority of you, if not all of you did, you should be familiar with limiting and excess reagents already. This is where we start off the year when we start talking about stoichiometry. But I do like to just go over it here because it is very important. A lot of problems that you're going to see in AP Chemistry involve limiting and excess reagents without the problem saying that it's a limiting and excess reagent problem. So you're going to see quite a few examples like this throughout the year, and I want you to get familiar with identifying limiting and excess reagents pretty readily. You should look at a problem, and if you're given the amounts of 2 reactants, you should be able to determine the limiting reagent first, even before you approach the problem any other way. Because like I said, they're going to be kind of involved in every problem, whether or not they say it's a limiting and excess reagent problem. So here's a great example, right? A problem might tell you you have 1 mole of nitrogen and you have 1 mole of hydrogen. How many moles of ammonia can you make, right? Or it might say, given you have 1 mole of nitrogen and 1 mole of hydrogen, how many liters of ammonia at STP will be produced, right? So it's not saying it's a limiting and excess reagent problem, but you have to recognize that it is one. So in order to identify the limiting and excess reagent, of course, we have to say how much of that final product can be produced from each of these. So how much ammonia can I make from 1 mole of nitrogen? And how much ammonia can I make from 1 mole of hydrogen? And this final number of moles of ammonia depends on the mole ratio. So based on this balanced chemical equation, 1 mole of nitrogen produces 2 moles of ammonia, and 3 moles of hydrogen produces 2 moles of ammonia. So because I'm starting with equimolar amounts, that's what this means right here. You might see the word equimolar, and that just means that they're the same number of moles, right? So because this is there's 1 mole of each reactant, there is an equimolar amount of each one. How much product can I make if I have an equimolar amount of each one of those, but if the mole ratio is different? So let's first start off with determining how many moles of ammonia can I make from 1 mole of nitrogen. So let's go ahead and we'll go from here to here first. I'm going to do that in green down here. And this is pretty simple because, let's see, I'm not going to write the formulas for them because I'm going to color code it instead. 1 mole of nitrogen produces 2 moles of ammonia. And if I solve for that, it looks like I would produce 2 moles of ammonia. 2 moles of NH3. So if I have 1 mole of nitrogen, that would give me 2 moles of ammonia. However, that's not taking into consideration how many moles of hydrogen are there. That's assuming that there's more than enough hydrogen there to react with all of that. So now let's determine how many moles of ammonia can I make from 1 mole of hydrogen. And again, we have to use that balanced equation using that mole ratio. So if I'm starting off with a 1 mole of hydrogen, it looks like here 3 moles of hydrogen produces 2 moles of ammonia. So that 3 and 2 right here, so this number and this number, and this number and this number, of course, are coming from the balanced chemical equation. And if I solve for that one, I get an answer of 0.67 moles of ammonia. So in this case, one of these equimolar amounts is going to produce less of that final product. So in this case, the amount of product that would be formed is the one that produces less. So this reaction would produce 0.67 moles. And that's because your hydrogen is my limiting reagent. So this is the limiting reagent right here. And that's because 1 mole of hydrogen produce significantly less product than the 1 mole of nitrogen. Then nitrogen, there's more than enough of that there to react with all of that ammonia, or to react with all of that hydrogen. So in this case, my nitrogen is my excess reagent. So just to get these down on paper, so we have definitions for them, what does this mean, right? Oops, what the heck? Going back to something I'm sure you don't want to do again. So let's go ahead and identify these. Hydrogen is your limiting reagent because it's totally consumed. It's consumed first in a reaction. And this prevents the reaction from proceeding or continuing. So my hydrogen is the limiting reagent because it produces less product, right? It's totally used up in this particular reaction. So hydrogen is my limiting reagent. It's preventing the reaction from continuing even more because there's no more of it left. Whereas my excess reagent is not entirely used up. And because it's not entirely used up, you're going to have some left over. So you're going to have some unreacted reactant left over after the reaction is completed. And we can determine how much of that excess reagent is left over. So I can figure out, okay, well, how much nitrogen is reacting? And based on how much nitrogen is reacting, how much nitrogen is left over? And that's all using stoichiometry. All limiting and excess reagents is just like stoichiometry on steroids, right? You're just doing a lot of stoichiometry problems wrapped up into one in order to figure out amounts that are produced and amounts that are left over. Like I said, I went over this in a lot of detail in Chem 2, so I'm not really gonna, this is gonna be a pretty short video just doing sample problems 9 through 11 here. But let's go ahead and do 9. So nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide at high temperatures. The other products of the reaction are copper and water vapor. So let's get the pen open here. If a sample containing 18.1 grams of ammonia is reacted with 90.4 grams of copper 2 oxide, which is the limiting reagent? So, first things first, we got to get a balanced chemical reaction here. So, looks like I'm reacting ammonia, again, which is NH3. So, let's get this reaction written out. 3. And I'm reacting that with copper 2 oxide, which is CuO. And it says let's see, nitrogen gas is being produced. So nitrogen gas can be prepared. So that's one of my products. And then it says the other products of the reaction are solid copper and water vapor. College Board actually doesn't care too much about states of matter, so you don't have to go crazy with states of matter either. I'm going to be a little more picky once we get to like solutions and all that, but for right now, it's totally fine that we don't include them. Let's go ahead and balance this. So I'm going to balance nitrogen first. Looks like I have 2 and 1, so I'm going to put a 2, make that guy a 1. Hydrogens, let's see. Looks like I have 2 and 3, which gives me a total of 6. Looks like I need 6 here, so let's put a 3. Then looks like that gives me 3 oxygens, so let's put 3 oxygens here. And then I need to put 3 coppers here. So it looks like 23133 is the correct equation there. So now that I have that, I like to just write down underneath it how much of each I have. So I have 18.1 grams of ammonia, and I have 90.4 grams of copper 2 oxide. Question is asking which is the limiting reagent. However, I usually like to read ahead a little bit just to see if there's a particular product that I need to determine the mass in grams for. And actually, if I look at B, B is asking how many grams of nitrogen will be formed. So I'm going to kill two birds with one stone here, and I'm going to determine how many grams of nitrogen. Reading B just allows for me to see which product I'm going to go to in order to figure this out. Because if I go to copper for A, and then I have to go to nitrogen to B, you're making more work for yourself. So I like to read ahead a little bit for these problems. Let's do some stoichiometry here. So first, let's determine how many grams of nitrogen can I produce from 18.1 grams of ammonia. So I'll do that in orange here. 18.1 grams of ammonia. And mass of ammonia is going to come here. Mass of ammonia, 2 moles of ammonia. 1 mole is 17.04 grams. Let's use that balanced mole ratio. So it looks like 2 moles of ammonia can produce 1 mole of nitrogen. And then 1 mole of nitrogen has a mass of 28.02 grams of N2. And if you solve for that, you should get 149 grams of nitrogen. So if I have 18.1 grams of ammonia and more than enough copper 2 oxide, I could produce 149 grams of nitrogen. However, I only have so much of that copper 2 oxide. I only have 90.4 grams of it. So now let's determine how many grams of nitrogen can I make from 90.4 grams of copper 2 oxide. So I'm going to do the same exact thing, just starting from the other reactant. Get a nice little stoichiometry problem here. Molar mass is 79.55 grams. That's a 5. CuO is equal to 1 mole. CuO. Cu. Okay. Mole ratio, 3 moles of CuO produces 1 mole of nitrogen. And 1 mole of nitrogen has a mass of 28.02 grams. When you do that, you get 10.6. So holy moly, that's a big difference, right? It looks like that 90.4 grams of copper 2 oxide produces significantly less nitrogen than that 18.1 grams of ammonia. So in this case, your limiting reagent is going to be the copper 2 oxide. So I'm going to circle this. I like to put an X over the one that I'm not making. So this one right here would be, can't make that. That's way too much. My limiting reagent, therefore, would be the one that produces less of that final product. So my limiting reagent is copper 2 oxide. And that's what the question is asking. It says, which is the limiting reagent? Let's just make a little note over here, just so we properly answer the question. CuO is the, I'll put LR, limiting reagent. Then it's asking how many grams of nitrogen will be formed. So it's nice because we just did that, right? So rather than going to another product, we already found this. So I'm just going to write 10.6. would be formed. So there was my answer for that one. Let's go ahead and look at sample problem 10. So it says, consider the reaction right there. Identify the limiting and excess reagents. So again, this one's nice because I do have a balanced chemical equation. And I do have right here amounts of each reactant. So I have 80 grams and I have 28 grams of carbon monoxide. I'm going to go ahead and color code these, and I'm actually going to just pause the video here so you can do this on your own. I'm going to do, actually let me figure out which one I want to go to. So notice how it does say determine the mass of iodine produced. So I'm going to convert both of these to iodine. You do have to convert them to the same product because you need a means of comparison. If you convert them to different products, I can't compare CO2 to I2, right? I can't compare apples to oranges. I have to compare them to the same exact thing. So I'm going to do two mass problems and color code them. I want you to try these as well, so you can pause this video and see if you can identify the limiting and excess reagent, and then restart this video and I'll have the answer for you. So once we do each of those mass problems, just doing some simple stoichiometry, we see that we do in fact produce two different amounts of iodine, and we are going to, of course, produce the amount that produces less. So in that case, I would produce 50.7. This one you can now throw out because it produces much more than your other product or than your other reactant. And it looks like carbon monoxide is going to be your limiting reagent right here because it produces less iodine. Question is asking here, identify the limiting and excess reagent. So I'm just going to identify them just by circling right there. So I'm identifying it right here. And this one right here, so this diiodine pentaoxide would be my excess reagent. That's good enough to identify them for now. Determine the mass of iodine that's produced. Again, we're going to produce the lesser amount. So in this case, I already solved that one, which is why I like to read ahead. And I have 50.7 grams of iodine. Next question is asking, determine the mass of unreacted excess. This is where a lot of students can have trouble, but again, if you know your stoichiometry and you understand this in your soul, then you could solve this problem. So we know that the excess reagent is not getting used up, right? All 80 grams of this diiodine pentaoxide is not getting used. However, all of this carbon monoxide is getting used. So I need to know, of that 80 grams, how much of this is reacting. And I could figure that out by doing yet another stoichiometry problem. If all of my CO is getting used up, because that's the definition of a limiting reagent, right? If I go back here, a limiting reagent is consumed first, prevents the reaction from proceeding. I could figure out how much of my excess reagent is reacting because this is totally getting used up, my limiting reagent. So I'm going to go from my limiting reagent to my excess reagent because I know I should not have 80 grams that's reacting. It should be less than 80 grams. So let's figure out, doing another mass problem, if I have 28 grams of carbon monoxide, how many grams of I2O5 is reacting? So I have 28 is the molar mass, happens to be the same. It's equivalent to 1 mole. CO. Looks like 5 moles, use that balanced chemical equation. It's equal to 1 mole of I2O5 and 1 mole of I2O5 has a mass of 333.8 grams. And when I figure this out, looks like that I get 66.7 grams of I2O5 actually reacts. So this is how much is reacting. This is not how much is left over. So we, however, have started off with a different amount. I'm given in this problem 80 grams of I2O5. So I have to consider that in order to figure out, well, how much is left over? So if 80 grams of I2O5 is available, I'll never get good at using this pen. And I just determined that 66.7 grams of I2O5 actually reacts. Then I could figure out how much is left over just by doing a simple subtraction. So 80 minus 66.7 tells me that I would have 13.3 grams of I2O5 that's in excess. That's how much is left over. You did a lot of these types of problems in Chem 2, so you should be familiar with them. We're going to do some practice with these in class, though I'm not going to harp on this for very long because I did teach this in Chem 2 already. Lots of practice problems in your textbook that I gave you with determining the amount that's in excess. Another very important part of limiting and excess reagents is determining a percent yield. And this percent yield tells us how much of the total did you actually produce. So if for example, in this problem, if I'm supposed to produce 50.7 grams of iodine, and I actually did this reaction, but I only produced 40 grams, what percentage of that whole did I actually make? What's my percent yield? That's what we're finding. And you did a lot of labs in Chem 2 as well, where you determined a percent yield, because this is a very important part of chemistry. If you're working in a lab, right, and you're synthesizing some new compound, some new pharmaceutical, you want to have a reaction that produces a very high percent yield because it's the most economically efficient, right? You don't want to have a very low percent yield because that means you're costing a lot of money in your reagents. And you don't want to waste money on reagents if you're not getting a lot out of it. So your percent yield is a measure of how much product was obtained in an experiment relative to theoretical calculations. So that would just be what I would get as a result of a mass problem. Oopsie doopsie. Here we go. No, let's see if I can get this back on the page. Nope, I think I'll just have to go down here. Let's say do this. There we go. Sort of. A little off there. It's fine. You get the idea. Actually, let me try to move this down. There we go. Perfect. So, looks a little different from your notes, but it's fine. So yeah, let's go ahead and try this. Here's a little equation for us, but you're going to do this so much in labs throughout the year. You should know this off the top of your head. Experimental yield divided by theoretical yields times 100. So methanol, also called methyl alcohol, is the simplest alcohol. It can be used as a fuel in race cars and as a potential replacement for gasoline. Methanol can be manufactured by the combination of gaseous carbon monoxide and hydrogen. Suppose 68.5 kilograms of CO is reacted with 8.6 kilograms of hydrogen. So, and it's asking calculate the theoretical yield of methanol. It's not saying it's a limiting and excess reagent problem, but it is a limiting and excess reagent problem. So first things first, we got to get an equation down. So let's do that. Let's see. Methanol can be manufactured by the combination of gaseous carbon monoxide and hydrogen. So carbon monoxide looks like it's reacting with hydrogen. to produce methanol, CH3OH. Make sure this guy's balanced. Looks like I just need to tack a 2 in front of my hydrogen there. So I'm also given amounts of each reactant or each reactant. So I have 68.5 kilograms of carbon monoxide, and I have 8.6 kilograms of hydrogen. Let's go ahead and I'm going to color code this again just so you see, but I want you to determine which is the limiting reagent, right? And even though it's in kilograms, it's fine. Ultimately, it doesn't matter because we just know, or what you should know, is that there is 1,000 grams in a kilogram. So I'm going to color code mine just so you could see the work for each of them clearly. And pause this video and you determine how many kilograms of methanol can be produced. All right, so there are my 2 answers for each of those mass problems. I actually left mine in grams only because this next problem, it's in grams as well. So which one is the limiting reagent? Or it does say calculate the theoretical yield. Your theoretical yield is whatever produces less, because of course that's from the limiting reagent. You can only produce whatever the limiting reagent can make. So in this case, my limiting reagent is the hydrogen because it produces less of that final product. So your answer is going to be this one right here. It's your theoretical yield. This one doesn't mean anything to you at that point in time. Next question is asking if 3.57 times 10 to the 4th grams is actually produced, what is the percent yield? So here's where that percent yield is going to come in. This right here would be the result if somebody actually did this in an experiment, right? So this is your experimental value. Somebody did this and they determined what that yield would be. And all I have to do is just determine, well, what's my experimental divided by my theoretical? What percentage of the whole is that? So my percent yield is equal to 3.57 times 10 to the 4th grams. And I'm going to divide that by 6.82 times 10 to the 4th grams times 100. Now, if you consider just a little bit of mental math, right? That 10 to the 4th on each of them cancels out. So this right here, you don't even have to type that in your calculator because that's going to cancel out. And if I look at that value, so 3.57 divided by 6.82 is going to give me about a half. Because 3.5 is 7, and you can see that that value is almost 7 as well. So it's going to be a little bit above a half because it's not quite 7. Just so if you do see something like this where it is asking you not to use a calculator, you can identify, well, it's going to be a little bit above 50, right? Without even doing any calculations. But that's not this type of problem. We can use a calculator. So if you just do 3.57 divided by 6.82 times 100, you get about a 52.3% yield. And you'll see it is in fact a little bit above 50%. Is that a very high yield? No, you only produced half of what you were supposed to. So if you were in an actual lab, would that be good? It depends, I guess, what you're making. But if your boss might say, what can we do with this reaction in order to increase our percent yield? What could we change? And that would be where the real fun chemistry comes into play. Like I said, I did teach this in Chem 2. This is a whole unit. So everything that I did here is a whole unit. So you can always ask me any questions. Those of you that are enrolled in Chem 2 simultaneously, we're going to do this very soon in class. But as always, please ask me any questions, take notes, make notes in your note packet on anything that you're confused about, and please ask me in class. This is a huge topic, so you need to know how to do this. If you are a chemist, you need to know limiting and excess reagents. Like, you can get away not being very good at kinetics, but every chemist, no matter what they do, needs to know limiting and excess reagents. So on that note, I will see you in the next video, which will be all about periodic trends and atomic properties. So I will see you then. Bye.